Assalamu alaikum and welcome to our channel. Today we would be discussing about the examples in chapter 9 and we would be explaining going through all of them. So chapter 9 is taken from AVI books of AVI books and its chapter 9's heading is AVI timer programming in assembly and C. So in this, we would be explaining about the timers and counters and all of their explanations, and we would be using flags, muxes, and oscillators, counter registers, etc., external sources, and everything else. So let's start with our example number one. That is over here. And the question is to find the value of TTCR0A and TTCCR0P. If we want to program timer 0 in normal mode, node preceder use AVR crystal oscillator for clock check a source. Now, what we have to do in it to select no preceded CS02 CS02 slash CS00 slash 001 and choose normal mode, that is WGM02 slash WGM00 slash 00. What we do first, the TCCR0A and then TTCR0 R0B. So in this, there would be only one change that would be coming over here, that in DDR0A, all of them would be 0. But in DDR0B, that is 1, and the last one would be 1. Then we have example number 2, find the timer clock frequency and its period for the various areas, the AVI-based systems with following crystal frequencies. Assume that no presetter is used. So first is 10 megahertz. Now the formula is frequency is equal to 10 megahertz at a time. Cycle is equals divided by frequency divided and divided T is equals to 1 divided by T. Time is equals to 1 divided by frequency is equals to 0.1 megahertz. 1 microseconds. Then if frequency is 8 megahertz, then it would be 1 divided by 8 is equals to 0.125 microseconds. Then if it is f is equals to 1 megahertz, then it would be 1 microseconds. After this, our third example is third example is really large and it has a solution in there as well. So in this following program, we have creating a square wave of 30 degrees Celsius, 30% during the cycle, and with the equal portions high and low on the both survive the timer zero used in the generate the time delay, analyze the program. So in this as we basically what we would be doing is that we would be creating a block cycle, a square wave that we generate in ID or oscilloscope as well. So for this, what we would do that we would be creating a dot, and this is a assembly language code. So we would be writing in assembly language code, and first we would be writing dot Marco LDI dot Marco in track dot Marco any stack initialize set of stack. We set any stack any stack. We set up a stack here LDR 20 is high, R LDR 20 LDI register 20 is high, that is means it is high, that SPH 20. It is basically we are creating a stack over here. It is a stack function. Then E and end Marco, that means that is when we started, we ended, and in each stack is then we have called again. Then what we would do, what we would be doing, we would be initializing the resistance R value is that one smallest one, one two the process zero the slash zero, and the smallest one of 5, that it means that it would have the value of the R16 is equals to minus R16 would be having a value of 1 to smaller than 5. Then SPI value or DDRB is 5, then that is the output at port 5. Port 5B is 5, and then LDI port LDI R17 is 0, then output port B is R17. That means that the clock is clear. First it was 5, then it 4, then it was cleared, and then we began to recall the delay. We got timer delay over here, and for this timer delay we use that EOR call R16 and R15 R6, that is toggle data 5 of R16 by XORing with 1 XOR 1, because say R16 we already know its value was 0 0 0 1 0 0 0 0 0. So we were toggling it with 17, so R17 is already all 0. So this one we would be XORing it with this one. So after that, this is the XOR function in XOR statement is written as EOR. Then it would be then the result of this XORing would be output displayed at port B, and then we would be re-jump to it to B begin. That is B begin is okay. The B begin that would be placed at the start. So after that, they have also given that today B begin today is equal to LDI after 20. Then R after its value sets, then output at TT timer 0. Then LDI is again initialized R20s, and again initialized as 0 0 means input, and then it would TDR E0A means port 0A is taken as normal mode, the TDR then DLDI is 01, that is the normal mode, internal mode, then it was also given to the DDR load B. It's more given normal mode, no internal clock without no processor, because 0 cos 01 is included. Then again function is called as an SPIS and DDR0 TV0 if TOV 0 is set skip next instruction to. So after this skip, it would be skip in next instruction, re jump to again, then it would be again jump to again, and this loop would make just walk out a work in this loop. It wouldn't get out of it. Then LTI R20 0 cross 0 0, the output of TDR 0 EE 0 TCC R or 0 E. It would be R20 stop timer 0. First was initializing, then it was stop. Then the LTI 0 is one, smallest one, then we are calling it one bin, and serial number, and then it's TIF R0 R20, then clear the TOV flag means the writing flag is down, and the program is ended. And then the next example is that calculate the amount of delay generated by Zoom with Crystal 5. Now, these are all examples going on, and their formulas are similar, but they have been given examples. It would be just first from the timer we calculate the hertz, from hertz we calculate the start seconds, and seconds after the seconds we multiply the number of counts to determine the delay, and when we have determined the delay, simple answer. So we would be checking it for its flags. Then the example in exam 9.3, calculate the frequency of the square root and generated in assumed word. So in this, what we have done, whatever the code we have written, now we would be generating its time delay. It's very simply easy that we would be jumped. There are certain examples, certain declarements that has 3 values, 2 values, and 1 values. I would be explaining you again. But afterwards, but some of the values have half value is half. Some of the function also have half as half of it due to its output that it is performing, and some has higher rate because of its for just like for RET, it's the result, its output, and it has value cycles of 4 to go on. That's why it is given 4, and it has 384. So it has an extensive code that has its own values, and where we would just simply calculate these cycles, and after calculating these cycles, we would be more plus adding it to 14. That is given over here, and multiplying it with 2, so and 0.062 microseconds, and we would be getting our answer. Then we would just like we converted in farad timer to farad, time to farad, we would be convert farad to time to we would be converting time to farad now. Then after this, the 9.6, we find the delay generated by 0, and in this just we are finding the delay using both the methods of the 9.8 9 do not include the overhead or due to instruction. What we simply do, the code is same as given below, but we have to now recall delay. Delay option that we would be having recalled in it. So now we would be recalling it by LDI R20 0 cross 0E. Now LDI's value is declared. Now output is TCT timer not 0. Timer 0 not would be having the value of R20, and LDI R20 is equal to 0 cross 0, so then outer diameter it is empty, so it is normal mode. First it is on, and then it is off, and then what happens when we are converting it to normal mode, the pre-setter without any clock, so it would be a delay function that would be incremented just like we had done increment and discrement. Now we had again SPI CTR0 so we is if TV 0 is set, then skip to the next instruction. Means that until analysis is not this is not TV T0, we TOB 0 is not set. It would just roam around in this loop, and it would just jump again and again, or otherwise as soon as this is 0, this will skip this term, and it would go to this term, and the LTI would be 0 0, and it would be output would be stop the timer and simply clear the bits flag. Then after that, assume that XTAL is 16, write the program to generate a square wave with preset of 16 megahertz of the pin. So first, in the first one, we had written, we were not given the instruction of how much delay we have to do in board B, but now we have given it. So first, we would calculate it, but first we have we have time. So we must have time delay, or but we half it, because this is the complete time delay. We must have the half of it, so we must have for square wave it would half be made by square half square and then half square. So it for this we would be having a time delay of 3.25 to and because of the external 16 megahertz, the counter counts would be is equals to 0.065 0.00 65. These are the counter counts of it of 16 megahertz, and now we know. Now we would simply be calculating it, that 3.125 divided by 0.00625 microseconds. Then 50 clocks, we get the answer. Then 256 minus 50, then we get 206 clocks. That is 0 plus CE. We have got the clocks. We have done the T and TC and T0 value. That is the zero code. Zero code. I'm saying that is the timer load. Zero timer load. Zero value we have declared as uh, uh, 0 cross CE, and now we would be simply making a stack. We would be making stack LDA values the same 16, but this time it would be smaller 3, because we have already done it. 3 value SPI value RB3 LDI 0 5. We have done this. Now we would be recalling toggle, then EOR. We would be recalling all of this the same as we done before, but now for the next thing, what we would do is that instead of it, we would be declaring R20 is equals to R0 CE, and then we would be TN0 T2 we would be 20. we would be loading timer 0, and then we would be making it normal mode, and then we would be normalizing it as going the same and the same connections that with the program that were given below. Now what we have, the examine the XTR is equals to 16, modify the program in the example 927 to generate a square wave of 32 frequency in port C. Now we know that first of all, the task we were given to generate or modify the program. Okay, so TF is equals to 1. Okay, so what are we going to do is our t value is equals to 1, but we find out the frequency is equals to 32 kilohertz, and 32 kilohertz is equals to 31.25 milliseconds. Then 1 divided by 2 is the high and low portion. So 15, this 31.25 is equals to divided by 2 is 15.605, 6525, and then we already have 625 to 16 megahertz, and 16 megahertz is equal to 0.025 megahertz microseconds. So 15.625 divided by 0.025 microseconds is equals to 250, and 256, and that is total minus 250. 250 is equal to 6, which is hex value of 0.06. So T and TCN T0 is equal to 6. It's simple. Then example 9.9, to get the largest time delay possible, find the delay in your calculations and exclude and overload due to instructions in the loop. Okay, so in the above code would be the same, but what we would do is first we would in we R20 is equals to 20 and 00, so we would load timer 0 with 0. That would be highest, and then but we again it was 0, so it would be the normal mode, and then timer we get the same with no preset thing done, and now it would be great. So the change that has happened over here is that we have already logged, we have made it 00. Now find the delay in milliseconds in your calculation. Largest time delay. Now if 0 and 0, they would never be matched. They would be a very long time delay created. The T0 means that the time delay will count from 00 to 0FF, means it would be such a large number. Then because it was 00, and then it will have to count from 00 to 256 values, and 256 values would be a very long time delay. So that is the largest that it could be produced. So after that, what we do is that at 9:10, now to this, what we would be doing, the clock frequency is find the timer's clock frequency and its period for various AVR based systems. So with the following crystals frequency, assume the presence of one one ratio 64 is used. So 8 megahertz, then 10, 16 megahertz, and 10 megahertz. What we will do with 1 divided by 64 multiplied by 8 megahertz is equals to 125. So 125. So now we have got this frequency would simply divided by 1 divided by 125, and then we would get microseconds. We would be explaining this in all the three, and we would be getting the answers. Then 11 find the value of TTR TCR05 if we want the program the time is now quite 0. So in this normal mode we with presenter 64 using the internal clock of the source. So what would happen? We would be simply connected, and now what we needed 64, a preset of 64. So for in 64 means that we have TTR 0 is equal to 0 cross 0 0 0 0 0 0 0 1 1. Why it is 1 1? So grade 64. And here we have this video. We have to see 9 to show 5 so figure to explain this. So we simply go to 9/5 figure. 9/5 figure. So this is over here. So it is already given over here that how you need to know about this diagram to know how to do it. So 964 we have to write is 1 1 at the end. This is over here 1 1. First we WG O0 was F bottom max and it is the sorry. We add the first ones ahead and 0 0 and then we make 4. 64. Hmm. 6 is 0, 1 1 0 0 and 4 was 0 1 0 0. So integrating it we get 1 0 0. Okay, after that we have 12th example. The following program the time today in seconds execute the overhead due to instruction in the loop assume that is 16. Now what we have done same code that we are repeating again and again and again, but now instead R20 is equals to R0 cross 10. Now why we have done is examine the following program and find the time delay in seconds. Okay, so this is the program that is given to us, and we have to find the programs in seconds. What and define the day time delay in seconds. Exclude the overhead due to it. Okay, so what we have that 16 megahertz is that TCN T0 is 0 for 0 cross the 1 0. So it is equals to 16 in decimals. When we convert this 1 0 cross 0 1 0, it is converted into 16 in decimals. So 256 minus 16 is 240. 240 is multiplied by 264 multiplied by 0 0.025 64 because it is 64 bit because we have 64 bit and then the 64 multiplied by 0.02025 comes from 16 megahertz. So it is 960. From this 960 we have the 960 multiplied 960 we have this that 240 multiplied by 4. That's this 240 is multiplied by 4 times 1 milliseconds to get 960. So 4 cycles are completed. After that, assume that XTL is R16. Find the clock period to feed in the presenter interpreter opinion of 102 chosen. Show that the largest time delay can get using this prescribed option and time test 0. Now 16 megahertz is equals to multiplied by 1 divided by 1024 as we have find the clock fed into the timer. 0 is the principal option of 201201 I will start it. So what happens that we multiply by 16 megahertz multiply by 1 divided by 1024 that was given to us as the pre-seller option. And what we scalar option, then the answer would be this 115, 66 to 5. And then what we do, the time is 15 with this hertz, with the frequency of 1565. 65 we divided by 1 divided by this answer, and we would get the time seconds of 64 megahertz, 60 milliseconds, and that is 0.064 milliseconds. To get the largest delay, to put TCN T0, the timer the load is 0, a time is 0 is equals to 0, and making this 0 means that it has to be calculating it can count it from 0 0 to 0 plus FF. So this then we roll over T0 TOV 0 as a result it goes from the total of 256 states, and therefore we have time delay of 256 minus 0 multiplied by 64 megahertz is equal to 16,384, and this is the seconds given to us. Then the same way, the next example, we have the program generate a wave to 250 frequency and the pin port P use the timer 0 mode to preset is equal to 256. Now, first of all, we would be calculating it times the 250 hertz. It is 4 megas microseconds. Then 1 divided by 4 is that because we need a square wave pulse. So it's 2 microseconds. Then 2 microseconds divided by 0.0255, that is due to the 16 megahertz frequency, the hertz frequency, extol. External, then divided by, then divide this whole answer by 256, we get 125, then 220, 256 minus 125 is equals to 131 in decimals, and in the hex value it's 0 cross 83, 0 cross 83. Then we have decided our t, and t 0 value is equal to 83. So we would we simply be putting its value over here, and for normal mode, for normal therapy mode, we would be putting it 0 was 0. If because preset is 256, preset is 256. Preset is 256. Then again, the diamond, the DOV flag is raised, and then it is clarified and cleared, and it is done. Then in 15, find the value in hex and dotted to say DC and TC and T0 for the value each of the following cases. LDI T20, LDI R20 is equal to minus 200. Minus 200 means that is second component complement. TNC, TC and T, as TC and T value becomes 0 cross 38, and then simply in this find the values in hex loaded into the so what simply we would be changing these 200 these values that are given to the different resistors into hex, and say minus 60 is equal to 0 cross 6 for C4, and minus 12 is equal to 0 cross F4 5 4. Then we have to find the frequency of the square and generally following the report code and the duty cycle of the wave. Assume this tolerate. Simply creating stack, then we SPI 5, then it as R18, R18 we calculate minus 80 150, and then we would be creating, and again high 40 TN 0 is equals to 80 R's 18, then loading time, load timer 0 byte, timer 0 byte per byte, and then calling today, then again call 0 timer 0, then today, then 4 to 5 CBI 5, CBI port 5. Port P is equal to 5, then CBI 5 is the fifth port of port of B 5 port B would be 0, and then T and TC and T0 is 18. Again reload timer 0 again today and then jump it to begin. Now timer 00, it is the highest timer we would be using, so 00 and 01, and it the timer TOV flag is on and off, and that. Now what we have to do, we have to simply calculate its 5. So 150 multiplied by what would happen 8-bit, and the conversion in run is only as long as we enter negative. We also have to make the calculations easy because we are using 15 kilohertz clocks. We use the time delay of submersion is 150. 150 multiplied by 0.0 cross 2 because it's 16 megahertz. We get a 9.35. So we would now what we would be doing now is that we're going to 66%. The portion of the pulse of the twice size of low portion. So what we get and what we had, we would be getting a 66% duty cycle in the time is equal to high portion, the slow portion is equal to 2 multiplied by the 2 that we had calculated before, to multiply by 9.34875 in microseconds is equals to plus the 9.375 is equals to 28 0.15125 and multiply this to this value. We do double its double its values, so that whole minus whole plus 9.6 it goes to 2.28.125 microseconds, and divided 1 divided by so we get 35.5 kilohertz frequency, and simply we make Then in the following program, we are creating a square wave of 50% duty cycle on the board. See, the timer T is used in the time to analyze the program. So in this, we have to simply analyze the program. In this, we first the stock is made, then the pin output 9 is loaded into the OCR 0A, and then after that TCCR 0 is loaded to the time delay 0 and started. Then the timer 0 comes up to the passing each of the clock in which is provided for the crystal oscillation. As the timer 0 counts, it goes through the states of 0, 0, 0, 1, 0, 0, 2, 0, 3, and so on. And as the timer counts up, so as one of the and reaches 9, one more clock rolls out of 0, rising the timer, comparing the match and of the match flag 050 OC5 OCF0A is equal to 1 at the point of this as SPIS diffro OCR OCF OA 0A instructs the vice versa jump again instruction the time 0 is stopped and OCFOA is cleared to previous one. Find the delay generated by the timer 0 in example 1917. Do not include the overhead due to the instructions. Okay, we had given 9 is included and here TC and T is cleared. So what we get TC and T0 is cleared after 9 plus 1, which means 10 because it was 9, it's highest number, and after that it was cleared. So 10 clocks we would be having in we have 16 megahertz. So 0.10 multiplied by 0.02 or 625 multiply करेंगे तो we get 0.625 megahertz answer. Among the delay generated by the timer 0 in the following the program do not include the overhead due to the instructions. Okay, so for first we have the value of 89 given over here, and then we have a value. Okay, it's GBGMO1 we use. So in this procedure, where what we will do, the 89 as well, as we have already declared over here. So what we have, due to the reseller, we have 62 each timer value clock last. So 64 multiplied by 0.0 or 2625, that is due to the extra electricity value of 16 megahertz, so 16 that is equal to 4 microseconds, and then OCR0A is loaded at 8 to 89, and after that 90 clocks are 90 clock is set. Therefore, we have 90 multiplied by 4. 90 multiplied by 4 is equal to 360. Then after that, we have tried a program to generate the delay of 112.7 use time 0 or more with the preset 10424. Okay, please that is 1024 last then multiplied by 0.0625. That was given our 16 megahertz. Then we get 64 mega microseconds. So thus, in order to generate the delay of 12.8, we should know that 12.8 microseconds divided by 64 microseconds is equal to 200 clocks. Therefore, the OCR 0A register should be loaded and 200 be always -1. So that we minus it from 1 from a 200 it would be 199. So in this code, what we would do, we will separate inside in the delay one. After the 0, we would be loading a timer 0. The value is T91199, and then the same previous code that was in the previous program would be implemented. Examine the explain write a program to generate the delay of 1 microsecond in the solution. So first we would be calculating the 1 microsecond millisecond. It's not micro, it's going to be milliseconds. At first we would be stating it as milliseconds, 1 millisecond, and then we would be making this program. First, we had none. This is only 16 megahertz. 16 by 1 divided by 16 megahertz, 0.0 is 625, and then 1 microsecond, 1 milliseconds divided by 0.06 seconds, we get this answer. Then, if it is 8 percent, then this value will become 864. We have 250. If 256, we have 62.5, and if 1024, we have 15.625 value. So one we in this question we have given not told about the preseller. So after that what we will do the above calculations, we have the preseller, all these preseller. Now what we would be doing is that we used on our opinion, we used the percent of 64. You can use any, and we cannot use a decimal value. So because both of the after 64, both the 256 and 1024 were decimal value, that's why we couldn't use it, and the we have chosen 64 is the most precise one. So after that, 250, its value was 250. 250 minus 1 is equal to 249. So we would be loading after 0 we would be loading 259, and here we would be loading 0 plus 03, just because of the 64 here. And then the next example. In the following program, how long does it takes for the PBS becoming one? Do not you include the overhead instructions. So first we would read the solve program, and we have to signify two things. That LTI to the second word part, it's like third line LTI R20 is 89, and then in the fourth one R20 value is 95. So OCR zeros value is 89, and TCNT 0 is value is 91. So moving ahead. So the solution. 95 and 89. We have taken the TCNT 0 value is higher than TNT. The timers go up until it goes to 0 FF and roll over to 0. Then our TOV 0 flag is also overflow, and then the timer counts up until the value becomes to 89, and compare the match of the occurs. Thus, the first compare matches occurs after 161 plus 90 is equal to 51 clocks, which means that 251 multiplied by 0.0625 is equals to 15.875, and 90 clocks, which means 90 multiplied by 0.5 is equals to 5.625. Okay. After that, find the value of TCCR2B. Okay, now it's 2B. Uh, uh, a normal mode and a special of 64 in 10 block. Now first, when we had sample one, in these we had to had 64 is last to JSON, but now we would be having one 2B, the system suddenly changes to CS22 as 1. Using a preset of 64 write program to generate a delay of 960 megahertz, assume the external. We have done this example before as well. So first we would be creating a time clock is equal to 16 megahertz, 16 megahertz divided by 64. That is are generated for seller, so we get 250. Then time period is 1 divided by 254 microseconds, then value the timer value is equal to 960 divided by 4 microseconds, because 964 seconds 4 seconds 240. So as we STS we value, we would be declaring R20 is equals to 240. Then after that we would be declaring loading it with resistor TC and T2, and then 00, then higher delay, then 2A, and then after 2A we would have to be 2B. So 2B we would, as it is 4 cycles, so it's 0 cross 04. and then DOV2 is the on, the flag is on, and then this goes ahead. So in this, it would the 25th example, it is using CTC mode use write a program to generate a delay of 4 milliseconds. In these seconds, assume x star is equal to 16 megahertz. So in this, we would do again what we would be doing is that we would taking time series, the timer clocks, and then we would dividing it by 8. By simply by the clocks timer presets, and then we would do getting answers. We were skipping the high. We were skipping the one with the one with the decimals, and so the we what we got was 256, and then we said that was 256. Then 256, we got an answer of 250. So 250 minus 1 is equals to value of O, or OCR2 is that is to 249. And then instead of that, instead we have done in this in 6 cycles, and then we would be simply changing the values of T20 is 249 and 0 and 006 at the required places. Example 26. Find the values of TCCRIA R1A in TC1RD. In the program timer 1 input 0 with no preset. The means preset is equal to 0. Use ABRS for the oscillation group sources. Okay, so TCC R1A is equal to all 0, and TCC R1B is the last one is 1. So VG is 0, VG MVG1 VGM 011 is equal to 0, but VGM the 13 is also is equal to 0. All of them are 0, 0, so the oscillation clocks have no precedent. As it is no precedent, no. Okay, find the frequency of the square wave generated by the following program of extra crystal of 16 megahertz. And in your calculations, you have to include the overhead. Okay, not we have to not have to include the overhead. So we would simply be going reading the program, and we get from the program that it is based on timer is mode is 0. Okay, the first time mode is 0, and then the top is 0 cross FFFF. So FFF plus 1 is minus D850 is equal to 0 cross 2710. That is 10,000 clocks. That is 10,000 clocks, and then what we do that when we got 10,000 clocks in 16 megahertz, we have 0 cross 0 to point 0 to 625. So we would be multiplying this 10,000 clocks with this 16 megahertz, and we were getting 65 milliseconds in that is microseconds. And then we would what we would be doing that we get the frequency. First of all, we would be converting it, as we know it's a square wave, so it would be multiplied by 2. It would be multiplied by 2, and after that multiplying with 2, we would be dividing 1 with this answer, and then we will get 800 microseconds, 800 hertz. Okay, then we get 800 seconds. In this calculation, we have missed, or not overheaded. So, now we notice that instead of using hex numbers, that we can also use high and low derivatives as shown below. This is the one we have to do, and then after that, We have example 28 that RC we have to define its value, and this time it has in mode 4. In mode 4, what we would do is that our VGM12 value is equals to 1. Okay. Now presenter included source code, and then what we have are E1, one A is equal to all zero, but one B is 0 0 0 0 1 0 0 1. That we get on the table. Right, right. Then we have to find the frequency of the square when generated in the following program. Okay, then now is 151. We have 159. Okay, and one. So first of all, what we do is that we get we calculate our VB13, well VB13 which is equals to 10, which is 10 is equals to 10100. That is 0 was 04 in hex. Therefore, the timer one is working in the mode 4, so we can say it's the mode in it. So after that, we 159 we had that which we had detected over in the code. So 159 plus 1 is equals to 160 clocks, and next order is equals to 16. So 1 is 0.0625. Then they multiply 160 by 0.0625 microseconds. That would get 10 micromilliseconds. And then for getting the frequency, we will 1 divided by its answer multiplied by 2. So we would be getting a 15 megahertz, 15 hertz frequency in this calculation. Now this is the question that we get 16 crystal value 16, write a program that toggles P5 once per second. Okay, so in this we have to this, as we know the toggle, we know the toggle we takes, we know how much it takes for 1 second. Now we need that for 1 second it's 16,000 clocks, and that is 0 x 3 e 3 e 0. So now we include that our ORC, we need 16,000 clocks for the OCF1 E flag to rise. So now what we would do is that we simply go there and we make a stack. And after making a stack, what we would do is we would be making first we made the stack, we made SPI 5, the fifth port of for port 5 is input, and then we began the SPI 5 delay recall NMS, recall delay NMS, and it would again IMS. So the big is it is jumped to delay IMS, and for this we have first the largest value, then LDR, then temp is equals to 0, or temp is equals to 0, and TC NTIL flag would be 0 as well. Then TCNITL flag is also is equal to 10. Then afterwards we had another LDI R20 is high, and that is 16,000 minus 1. Now declaring that value 16 with 16,000. OCR 1A 1EH is equals to R16. Then LDI value of R16 low also R16,000 minus 1. So um, it's also initialize its value. After that, same 00 TC is equals to R20. R20 is already stored as 116,000 minus 1, 16,000 minus 1, and VGM 11 is equal to 10 is equal to 00. So after that, we will also then minus 9, because 9 frequencies were needed to complete it. So VGM 13 is all 12 is equal to 1. And then we simply move with this in a gain loop, and it would go round and round. and then we make the ST stop the timer and then clear it. Then after rewrite the example 30 using TOV flag. Now what we would do instead of using the last ones, we would be using a TOV flag. Simple. We would be using a TOV flag, and then we would simply be going from TOV flag to stop the counter and start clearing the um, flag as well after the work is done. Now an LED is connected to PB5, assuming the crystal voltage is 16. Write a program to toggle this LED. First of all, we would see that we had no preseller, so we have to calculate the preseller. We have 16 hertz as the external load. The difference outputs of the presellers are as follows. We would calculate it, and then for the example, from the above the calculations, we have two options. One, either we have to the 256, uh, or we have 1024, because they both values are the minimum. The minimum other value is in millions, and these two values are less and less. So we choose 1024 because it is the smallest one. When we choose the smallest one value, now what we do after this writing, we instead of its value was 1565 6625. So we use the 50 instead of anything. We use 1565 625 over here, and as we know, it takes 05 cycles. So we also multiply in one. We multiply it by 05, and then the code is same for the rest of it. Then 33 write a program to generate 1 hertz frequency in PV5. Then it's same, we would go for all of the checking of the reseller, and for the reseller, we have we would optionally take uh, 256 as it is the minimum one, and it does not has any decimals in it. So we would taking it inside is 7812.5. It's value 31 250. So 31250 minus 1 would be included, and it has 4 cycles and fourth number, so it is uh 04 would be multiplied with would be initialized at R20 over here for the percentage one to choose the percentage. In this example, to find the value of CCR0, if we want to program timer 0 as a normal mode counter, use the external clock for clock source and increment on the positive edge. For the positive edge, no processor used an external clock source, normal one. We and it does not have the fixed letter as well. So it would be zero. All the first four are zero, and then it would be 011, and it would be answered. Then we have 35th example, using the normal, assuming that the 1 hertz clock frequency is is fed into pin T0, and write a program of counter zero in a normal mode to count on a falling edge and display the state of TC and T0 and count the put C. So what we would be doing is, at first we would taking a CBI DDR direction is 4. So make T0 is pin PD4. Input means pin 4 of port D would be make as T0. Then LDI R20 is equals to 0FF, that is read, that is output port, and output DDRC is equal to 20, that makes port C is equals to 20 as an output. As an output port, then LDI to R20 is equals to 00, and then as the output TCC R0 R20, then input would be from TCC R0A. Then LDI is equal to 06, then counter falling edge is R
TCCR 0B. Then and again in input we do input from TC and T0, and then output we do at port C. So we from the serial ports we do the input, and the output would be done from port C R20. Then run to jump again. Then out of the 36 ensemble, after assuming that the value of 1 hertz is fed into the pin, T0 use the T0 B flag extended to time 0 and 16 bit counter and display the counter on port C and port D. Simply where LDI R19 0 and simply R16 is equal to 0, make time is 0, pin B, pin 4 of point port P, and then we make the output port C as output, port B as output, and then we what we would do TC and T0, we would take the inputs, and output would be shown on to R20, R20 and SPI, and flag of TOV0 would be raised, and then it would jump again. It would move in loop all the time, taking the inputs and outputs, and then moving ahead and ahead until and unless this would be condition would be satisfied. Then the LDI, and after this condition is satisfied, it would skip our jump and it would move to LDI. 16 one is then cleared. This means that clearing the flag of TOV0, and then out of and then we would be doing that we would increment R19, that means adding one number to R19, and then it would be implicit at R the port B, and then jump to. Okay, then is a 30 says assuming that the clock pulses are fed into the pin T1 and write a program for control counter in the normal mode to count the pulses on the falling edge and display the state of TC and T1 count on port C and port B. Okay, so what we have to do is make the DDRD 5, then 20 FF and DDRC 20 are the output DDRC. Okay, we have declared our port B, port C and port B as output, and then we have taken the input from TT and TTN T C N T I L. Okay. Okay, so after that we have taken a gain function, we have made an again function, and then LTS values R20 is NT TCNTI T1L, that is temporary also equals to it, and then output port C is R20, so R20 value is implemented from RT TC port C, that was taken from TC and TL T1 L. Then this LDS we declare its value to it H, then that is temporary. R20 is equals to temporary, and then output port B would showing the temporary value. Then the TOV flag is raised, and then this function is moves again and again until this satisfying this condition is satisfied. As soon as this condition is satisfied, it would skip to the next command, and it would lower the create flag OTV OTOV 1, and then simply we would keep doing it again. Okay, so after that, what we have to do is we assuming the pulses of the fed to be buzzer connected to the pin and write the counter of 1 and 0. So other than that, the counter the code would be remains remaining the same as we know. That we have 100 pulses. 100 minus 1 is equal to 99. So they had 99, that is 63 in hex. So we need 63 hertz be raised in head. So after that, we what we do is that its cycle is zero cross. Its pistol is zero cross zero e. So it would be declared with the heat is counter falling it would be given to it, And then we would be declaring 20 values first as 0, and then for making it temporary, and our CL is the our OC real value is 99, and then after that we would be raising its flag until it's done, and then its flag is removed. Okay, now we have to do use time delay in it. So what we will do is that in now this is a C code. So what we will do, port B 00, if I hit need to time delay, and then toggle it to 0 and that's it. So time delay we have TC and T0. TC and T0 is equal to 0 cost 20, and TC and TCCR 0 is 0, and then TCCR that timer non-zero. First we load time as 0, so for the high state, and then we get it the normal mode and no presellers. Because no presellers we use it was one a while loop, we add while loop and wait for the timer to roll over again. And after that rollover again, we simply write it TCC ROP is equal to 0, and TIF R0 is equal to clear the top. After that, 9 to 40, example number 40, write a C plus program to toggle only the port 4, port B 4-bit continuously in every 30 milliseconds using the time C. Okay. So in this, first of all, we would calculate it. For calculation, by the calculation, we get that our resultant answer is 186. So for this 186, what we would be doing is that this will remain same, but in the time delay, just there is a change in the TC and T0 value is 186. So TC and D0 values are just declared, and other than that, the value the program is same for the first one that is previously explained. Now, again, but this time it's 16 megahertz. Uh, 4-bit continues, so 1 millisecond. First one, the previous one was telling us about 35 microseconds, but is this 1 millisecond? So we do calculations, and after the calculations, we get a zero, the 0x 3 E80 clocks, and that is equals to 0 plus C180. We had. We have already covered these calculations above while doing it in the assembly. That's why I'm not repeated over here. We would simply be attempting its value over here in this 0 and 8 zeros value, that is the remaining 2 0 value is the higher would be it displayed stored in TC and T1 higher, and lower value 80 would be here, and then the same would be given as. Okay, then now the C plus was right, 4-bit continuously with every second. Now it is every second. Now what we would do, we'll check for the presellers, and now normal mode and 1 to 148, so 1024 divided by 1 divided by 1024, and then we would get this answer multiplied by 0.06 for the cluster value, and we got 64, and after the 64 divided by 64 is equal to 15,625 clocks, and that is 03x is 0, and after that we get a final answer of 0x C25 to F7, and what we would do further, higher would be C2 and lower would be F7, and that would be the only change on head. Other than that, the previous code will, and it would be the same like previous. Now 43 example, assuming that the one has the passes fit into the pin and try to extend the 0 and display it on the port 3 and port C. So what we do, we'll simply take port D is smaller or than 4. That means was it is written over here that we have to fit into T0, and we want port D. Pull up to pin 4. Then DDA direction of the DDRC is equals to 0 0 cross. FF means the port C is the output and port B is also output. And then we take the input, the out clock source as an input. Then what we do, we use a do and while loop. Do and while loop, we do port C is equals to T and TC and T0. And while TIF are 0, 0 cross 1, so means that wait for TOV to set. And this TOV, the flag is only raised until unless it will counted back to it. So TIFR is equals to, we also then clear this flag completely. And after this is raised, this is raised, it would come out of the loop, and after this clear, it would clear, this command will clear it, and the board B would be incremented. And then we go again. Then it is same as going the before, and then we would be going again and again, do it do while blow, place the pins, and same to go. Thank you very much. If you liked my video, thank you very much, and Jazakallah.